Okay, I should probably make a start. Okay, first of all, thank you very much for being here, the last session of the day. I appreciate it. So I'm Chris Adeni-Jones. I work for ARM in our Architecture and Technology group in Cambridge. I'm more of a software guy, so I'm not a deep hardware design guy. And today I'm going to be talking about some work that we've done to look at how you develop and deploy software for hybrid systems today and how we might like to do those things. So first of all, I'm going to very briefly talk about what a hybrid system is in our definition, why people would want them. I'm going to talk about the work that we did and then some of the challenges that we found, and finally a kind of hopefully vision for where we might get to, and hopefully at the end time for questions. So starting off, what do I mean by a hybrid system? So simply a hybrid system, as far as this work was concerned, is a system that has more than one different type of processor in it. So there's an example here of a generic hybrid system, has some application cores running Linux. Right over on that far side, it has two MCU style cores, one of which is running an RTOS, one of which is running a bare metal application. And then in terms of the memory map, you can see that each of those execution domains, each of those different kind of processor types has some of its own memory and has some memory that it's sharing. So, you know, they might be sharing between the RTOS and the Linux application. They might be sharing between the bare metal and the RTOS, for example. At the bottom, we have some devices. Again, typically the devices might be assigned to different execution domains along the bottom. And then at the top, we've got this generic shared platform infrastructure. Things like clocks, power control, again, shared between the domains. So why would these systems exist? So what we see along the computing continuum, right from the cloud native end, where people are used to using Linux, they're used to using containers, they have this very portable workflow and portability expectation. And so in terms of, you know, developing and deploying, that's become a very powerful paradigm. People are used to, you know, CI/CD, containerized deployment. That is all, it's not done, but it's very powerful. At the other side, we have deeply embedded, where everything is a little bit more controlled, constrained. Everything is optimized specifically for a use case. And again, people are used to that. In terms of deployment at that end, sometimes it's very one shot. You deploy it and then you forget about it. It just does its job. You never need to touch it again. And then as you move from either side towards the middle, or especially from the deeply embedded end, their expectations for deployment are increasing. So you need to be able to do updates for security, for example, or to improve the functionality, or in the current AI world, to change the model to make it better for whatever particular thing. So as you go towards the middle, you're seeing more of a drive towards being able to do those things. And so in terms of the hybrid systems, we see that there's this kind of portion in the middle between what I'm calling embedded IoT and cloud edge IoT, where people are beginning to develop these SoCs that have both the elements from application side and deeply embedded side, or the embedded side. Okay, so what did we actually do? What we decided to do was to take a board. This is the board, the IMX8M Mini EVK board from NXP. As you can see, this is what's inside it. So in terms of applications, it has 4 Cortex-A53s. In terms of the MCU, this particular chip has 1 Cortex-M4. It has all the normal other things that you'd want in a, you know, like an edge board. It has Ethernet, has some UARTs, has 2 gigabytes of RAM. So in terms of an embedded board, it's quite powerful. In terms of a kind of cloud native board. It's more constrained, but still quite capable. I'm going to go through each of the elements here in terms of how we created the system software to run on the board. So first of all, we used Yocto. The support from NXP for Yocto was very good. The instructions were very straightforward. They've been continually kind of keeping up with new Yocto updates. And it worked very, very well. So that's good. This board was actually one of the first system-ready IR certified boards. So that's probably helped. As well as using just Linux, we wanted to use these two pieces of functionality that Linux provides. One is called remote proc. So remote proc is a method where you can use the A cores to control the remote processors. So it lets you load a firmware, it lets you start and stop a remote processor. That's currently what it does. That might be something that we want to change. We also used virt.io. So the virt.io, again, that's provided in the kernel, so that we could use RP message, which is a framework that uses our virt.io as a transport to allow communication between the A cores and the remote processors, both ways. We needed to configure the device tree to ensure that Linux knew and remote proc knows that there's an M4 there where the shared memory is that we require, where the mailboxes are and stuff like that. So this is how remote proc and RP message work. You can see, remote proc is just in the kernel, and then it's using the kind of hardware features to, control the clocking and the power for the remote processor, talking to the shared memory, using interprocessor communication, which could be a simple mailbox or some other more complex device. And then RP message is built on top of virt.io, again, controlling the shared memory, using IPC. And then on the remote processor side, you run your application, you can run your application within an RTOS, or the whole thing could be bare metal. You use RP message again to communicate. So again, out of the box, that all worked fairly well. In order to write the application for the M, we used the NXP provided SDK, MCU Expresso. That gave us access to their included FreeRTOS. Obviously includes the peripheral drivers and has support for the board. One thing we do notice, again, is that the configuration used for the M is configured with various configuration files in the SDK. So again, you have to specify your memory map. You have to specify whether you want, when you do your final linking, for example, whether you're linking to run out of the tightly coupled memory or the external DRAM, which peripherals you want to use and stuff like that. The SDK supports power management so that when you're running applications on the M, they can be aware of the power state of other elements of the system, which is quite good. And can even wake up different parts of the system. In terms of IPC, we use the NXP implementation of RP message, so they provide an optimized for MCU implementation of RP message. And again, that just comes with the SDK. So in terms of our demo application, we took an application that we have already that we generated as part of a project called Smarter, which was simply about deploying using lightweight container orchestration to these kinds of edge nodes. So we took the same application. It takes input from a camera and from a microphone, uses machine learning to do some object detection, and then in the Smarter version, it actually uses FluentBit to send information to the cloud where you can visualize it, look at Grafana dashboards and stuff like that. We just kept everything local to keep things simple, so you could just use a local way of talking to FluentBit. And we also didn't use the audio side, so we were trying to keep it simple. In terms of the FreeRTOS application running on the M4, what we decided to do was to just create a very simple proxy application. So all our M4 application does is it writes a timestamp to a log so that we can see that it's still running. It periodically checks to see whether the A53s are awake or asleep. If they're asleep, it wakes them up. So it's a very simple proxy for something where you could put the A side to sleep, lower your power consumption, have the M do some more realistic processing, it might be doing some voice recognition, hearing a wake word, determining there's something happening, so it would wake up the wake up the A side, and they would do something. One interesting thing we found was, which was a bit of a surprise to me, was that we did actually need to apply some patches to the ARM-trusted firmware and the Linux kernel. Now, to be fair, these patches were provided by NXP. There were pointers for when I went and looked up to why this wasn't working. Out of the box, what would happen was when you suspended the A53s in Linux using the normal kind of suspend commands, the M would also go to sleep. So they were just coupled together. That was the default. And also, so the first patches were to fix that, to decouple the A53 and the M clocking scheme so that you could suspend one, not the other. And then we also needed to make sure that essentially the plumbing for the waking up when the M4 decided to wake up the A53s was routed correctly so that the A's would wake up. Just a brief mention of K3S. I mean, it's lightweight Kubernetes, it's open source, it's compatible with normal full-strength Kubernetes, so you get access to that whole tool ecosystem. The thing I really wanted to point out here is that applications in Kubernetes in general are implemented as pods, which are essentially sets of containers. And all the containers in one pod execute on the same node, so you can guarantee that they're all running together. So because of that, we were able to enhance K3S just using the normal configuration. We created a custom runtime class, and then we were able to add this runtime class to the pod description to say, for the normal containers we had before, we want to use the normal low-level container runtime runc, but for this new hybrid container that contains our FreeRTOS application, we want to use a different runtime, a new runtime, which we're calling the hybrid runtime. So basically, you tell K3S that's what you want to do. You then configure containerd so that it knows when it's told, I want this hybrid runtime, how to find the low-level runtime control and start everything up. And so eventually, when the pod is deployed, the containerd on the board is deciding, okay, for normal containers, I run them with runc, and for the hybrid container, I use the runtime that we've created, which ends up using remote proc to start the firmware. We implemented a number of checks in the runtime to ensure that the firmware was compatible with the MCU that we found or that we knew was there, and stuff like that. And also, if it's already running something on the M4, we would provide some kind of error message. So in terms of the gaps that we found, this major one is that the partitioning of the system is split between Linux and the device tree, and some of the policy decisions that are being made in the source code in terms of clocking and interrupts and stuff like that, and also the FreeRTOS SDK configuration files. So if you wanted to change, for example, the shared memory that you were using, the range of it, you have to change it in both parts. Otherwise, things are going to go wrong. The other thing is that the configuration is static. So, either at compile time, you're baking it in, or at boot time, and then it's done, you can't change it. One particular complaint thing we've noticed is that the names of things in Linux device trees and device drivers are very not standardized. So we looked at a number of different SoCs from different vendors that had Cortex-M as well as Cortex-A, and the Cortex-Ms were in the device tree, but they were called something different. There was no naming schema. And so if you were trying to look through the device tree to find a particular thing, it made it much more difficult. And this is coupled with a general, lack of discoverability. You have to know what you're looking for. You can't just say what's there. So 2 things to mention. One is the OpenAMP project, which is a Linaro community project. So it is designed to fix some of the problems I've talked about and to kind of provide a standard mechanism for some of these things in terms of allocation of resources, how they're shared, how you work out the communications and stuff like that, how you start and stop the runtimes. Again, under the hood, it's mostly using remote proc and RP message, and so is at one level, it's limited by what's there already for those things. The other thing I wanted to mention is the system device tree effort. So system device tree is an effort to extend the device tree specification to make it more amenable to handling heterogeneous SOCs. So not just describing, the small area that has the application processes, but being able to describe the whole system. And then also being able to describe the partitioning you want. This is all having to be done within the kind of limitations of the device tree spec, essentially. So the kind of paradigm for system device tree at the moment is you take a system device tree and you transform it using various tools into a device tree that you want. So, one for Linux, for example, one for U-boot maybe, one for something else. And it is part of the OpenAMP project. The challenge, there are still some challenges. So OpenAMP, the reference platforms, there aren't that many. It isn't very varied. Basically, there's a number from AMD with good support. There's 1 or 2 from ST Micro, but then that's it in terms of out of the box. There's some challenges in terms of RTOS support. So there's no OpenAMP implementations for FreeRTOS, for example. So you'd have to port that yourself. The system device tree work is a work in progress, so we kind of understand that. But we do think the device tree transformation paradigm is still possibly problematic and maybe not high level enough to make it truly useful. So in terms of our investigation, this is the kind of world we see at the moment. This is, we have 3 different developers. One's using the Linux toolchain to develop their application. They have to have the right device tree. The person using an RTOS has their own config. The person writing a bare metal application has their own config. And basically, they all have their own view of the system. It's very, very siloed. What might be better eventually would be to have a way to describe the system and to describe the partitioning of the system that's kind of independent of specific implementations. So to have a way to generate those configurations and a way to do it in a way that provides each application, each developer, a shared view of the whole system. So they're not just seeing their bit, they're able to kind of make some, have some visibility of the other things that are going on. But we're not there. Okay, that's the end, and now it's time for questions. Thank you. Thank you. I think Dara had a question.
So you showed on K. Did you look at K0S?
Yes, we have heard of it. We haven't used it. Do you have experience of using it?
Yeah, that's why I wanted to get your opinion if you tried it. But if you go back to your container D and you showed there, you made this shrim Yeah, what was wrong with, let's say, like extending container D for the functionality that you had on this hybrid implementation?
So, I mean, so Containerd already has the ability to run to choose. Sorry, you already have the ability to tell Containerd, I want this runtime, and it's already choosing a particular shim.
Okay.
So, I have glossed over some of the complexities here because, in reality, all the containers in a pod have to use the same runtime. Mm-hmm. So this would actually have to be two pods, one with all the run C containers, and then a separate one with the hybrid application. But I mean, you are still able with our configuration of K3s to make it easy to run those on the same node.
So then you would have had two pods here.
Yes. Yes.
Right.
Yes.
And if you go back to your story regarding the microcontroller, the Cortex M4, and you mentioned like you would want to try with different socks. What was your experience there in working with that microcontroller? Did you try to achieve this with, let's say, still an IMX8, let's say mini, but on a different ODM like a solid run or 80-link, and then see what does it take to port that interface? So
we tried with a different version of an NXP IMX board. So this is the mini that has 4 A53s and an M4. There's a Quad Plus, I think, that has 4 A53s and an M7. Yeah. So, for example, so that's where we wanted to make sure we could detect what MCU was actually there and ensure that the firmware you're trying to the application you're trying to deploy to the M is compatible. Yeah. So we did try doing that, and that wasn't. Once we knew that we had to do the check-in ourselves, that wasn't too onerous.
Okay.
But you do obviously you have to compile the FreeRTOS application specifically for M7, yes, and specifically for M4.
Yeah, I think that's fine, but it's from the operating system, from the visibility of that that there's a micro also there that you utilize. Do you think there could be any standardization to have that detected natively in the system?
Yes, it's probably more a case of deciding who or what is the right body to try and standardize that kind of thing. Yeah. But it would definitely be useful.
Yeah. Because exactly on that topic, that's where I'm still on the bench. I don't know if it's a system-ready kind of a story, or if it's an ATF story, or where we are, or TCG or whatever I think the other goes.
Yeah, no, it's right. I look forward to your suggestion.
I'm asking you too. Okay.
Yep. I guess it's a follow-on question from that, from Dara's, that when you're talking about describing the M4, are you just describing the fact that the processor was there, there's the interface, this is how you talk to it, or would you eventually want to have something in the device tree that says what is the function that has actually been deployed? Because if you're looking for like a general OS distro, you might know there's a processor there, but you don't know what it's doing, so you don't know how to talk to it. Yes. But that's a whole new problem.
Yeah, no. I turn it off somehow? Yeah, I mean, that's absolutely right. There is... Thank you. Yes, that is a good point. There would definitely need to be levels. The first level is we just know it's there. But there's another level of actually we know it's there, but I mean, some of it comes down to the partitioning. We know it's there. We know that it wants to use this range of memory for communicating with us. We know it wants to use these specific peripherals in order to do its work. So, I mean, even the NXP, the SoC, it has I think it's a trusted resource domain controller or something. So you can, in theory, enforce in hardware some of those decisions. But it's not straightforward. The kind of the TRM pages for that are many, 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 many pages. And so having a way to abstract that, to be able to get some of that information or specify some of that policy at a high level, and then someone else one person only has to do it once to implement the way of taking that high-level description and implementing it would be great. Yep.
The system device tree, so for the Linux, you extract the Linux part. For the Cortex-M, if you're using Zephyr, that also uses a device tree. Now, in the system device tree, I guess, like if you have an I2C peripheral, that can be used either by the Cortex-M or by the Cortex-A. You want to describe it only once, and then have another DTSI that specifies how the assignment is done. But that means that the core node has to be described in exactly the same way for Zephyr and for Linux. Do you know if this is going to be okay, or are there too many incompatibilities there already to make that work?
I think in theory it should be possible to make that work because, you know, in theory you have a tool that takes the system device tree and spits out, you tell it the partitioning you want, and it spits out the Linux device tree, and it could spit out the device tree for Zephyr based on the same information that you've told it. So it could decide, because you've told it a particular thing, it's putting that peripheral in one device tree and not in the other. But in terms of sharing, I mean, you would have to be in both device trees, and you'd have to have a different mechanism for deciding who's using it at any particular time. I guess you could use overlays or something.
That's what I meant. What I meant is, you want in the system device tree description, you want to have to have this node only once, because there is only one peripheral.
Yes.
I2C1. But the properties that are expected by Linux and by Zephyr are perhaps not the same.
Okay. I think some of that, essentially some of that information would have to be added by the tool that you're using that knows how to make a Zephyr device tree or a Linux device tree.
Yeah, that sounds like a binding problem of different bindings were created, and probably the way to fix that is change the binding. It's probably easier to change the M-class binding than it is the Zephyr binding than the Linux binding. But if you want to use one node for both and it go either way, really you got to do that. Or put the properties for both Linux and Zephyr into one node, which is just ugly.
Thank you. Any other questions? Oh.
Yeah, still on system device tree. Up to your view, what are the missing parts in system device tree from your experience? What was lacking in system device tree for what you expected to do?
I think, so I didn't actually do the system device tree work, but from what I remember, it is still fairly low level in terms of what some people might expect from a system description. And so that possibly made some things more difficult. Yeah, so there aren't that many tools, so we were using the Lopper tool to do some of the trials, and I think we found some limitations in that, but they could maybe be overcome. Yeah, I think that was probably it. It's probably not, in some ways, not high level enough in order to describe. You know, you might want to describe different partitionings of system that are, of resources that are not natural for device tree. You know, in terms of clustering or which things are connected via which buses. There were some things that we found not straightforward, not necessarily insurmountable with more information, but also the static nature of everything as well. You know, it's a beforehand thing, and for some of the more interesting use cases, you want to be able to dynamically discover and change things. you know, move a peripheral between execution domains and that kind of stuff.
Okay, maybe this is a bit beyond the system device tree scope, I guess.
Yes, yes, absolutely.
In your presentation, you mentioned this system device tree, and I know it can generate device trees for the several parts. And you mentioned also some bare metal-like or other environments that do not use device tree description. Is that you managed to build system configuration tables or blobs or whatever from a system device tree description?
Yeah, that's something that the system device tree people have. The people working on it, who I think mostly were from AMD Xilinx, actually demonstrated, probably at Linaro Connect or some conference. Yeah, so they were able to essentially generate a config. It might have been for FreeRTOS or it might have been for Zephyr or something. No, probably FreeRTOS, directly from the system device tree, and that configuration matches up with the Linux. You know, it's generated from the same source, and so you've got some. I think they even have a tool that can check the validity of those two things to make sure. So, yeah.
Okay, thank you.
About the dynamic device trees, there was a talk just before this one. You were there?
I was there.
Okay.
Yeah,
I see some overlap.
Yes, that all sounded quite interesting. There's still a question. Well, the device trees work for Linux. It's what you're going to do on the other side, for the other processors, where, you know, they don't have access to the same information, or at the moment. Yeah. So yeah, we did experiment with, you know, you can put stuff in a device tree that you can query at runtime. That's not. It's I can't remember how it's described. It's like an overlay, but it doesn't affect your Linux, but it's still there, and you can look at the information. That might be something that people do.
Actually, in Zephyr, the device tree is not used at runtime, only at compile time.
Yes.
So you anyway have different binaries. So
Yes. Yes, we did also notice that. Same. I mean, yeah.
Question regarding the limitations that you found with system DT. By any chance, did they report that on the Lopper GitHub? Because I think Bruce is pretty open to taking suggestions.
I don't think we've reported it directly, but I think that after this conference, the plan was to re-engage with the system device tree people and at least report those things. So yeah, thank you. That's a good reminder.
Okay, and I also have OpenAMP stickers. If anybody wants any, come see me after.
Oh, okay. Okay, I think we're done. Thank you very much for your time.